Hey everyone, in this video we will introduce the sort of last major topic for this class, which is the idea of sampling distributions. So we'll start today's video by talking about the law of large numbers and what that really says in two forms, the weak version and the strong version. And then we will define the idea of sampling distributions and how they may be used in practice. So let's start with the law of large numbers. And as you might have guessed from the title slide, there are two forms of this, a sort of weak version and a strong version. So let's start by just thinking about a sample. So we'll take a sample and we'll maybe continue to add observations to the sample. So we'll let the sample size n increase. We'll start with the sample n equals 1, n equals 2, etc. I'm going to define a variable s sub n as the sum of the observed values in my sample. So s sub 1 is just y1 alone, s sub 2 is y1 plus y2, s sub n is y1 plus y2 all the way up through yn. So what this law of large numbers really tells us is that the sample average, say y bar, or if you will, Sn over n, approaches the population mean mu as n approaches infinity. Well, we kind of knew that already. We've already shown using some properties of linear combinations that the expected value of the sample mean is in fact the population mean. So this in and of itself isn't really a new result. However, there are some differences here that we can work with. So we know that the expected value of the sample mean is mu. We've already shown this multiple ways. We also know that the variance of the sample mean is sigma squared over n, where sigma squared is the population variance. Now, we've shown a result related here for one particular distribution. We've shown that if our data comes from a normal distribution, if each of the yi's follows a normal distribution, then the sample mean follows a normal distribution as well. What we have really yet to show, or what we haven't discussed, is a few things. We haven't talked about the variance of the sample mean, what happens to that as our sample size increases. We also haven't talked about the distribution of the sample mean for other populations. Now, let's think about what this distribution of the sample mean looks like. So here we have some simulated data. This is in fact simulated from a normal distribution with multiple sample sizes. So here you see a sample of size 10, sample of size 30, sample of size 50, sample of size 100. This is simulated using a standard normal distribution. So the mean is 0, the variance is 1 for the underlying population. Notice what's happening to the variation on the sample mean. As we're increasing the sample size, these bell curves that are being produced narrow in. They become more and more and more narrow. This, in fact, helps us form or state the law of large numbers, and we'll state it in two ways. We'll start with the weaker form of the law of large numbers. So we'll let y1 through y2 all the way up through possibly y sub infinity be an IID sequence, IID here being independent, identically distributed sequence of random variables with finite mean mu, variance sigma squared. Notice that we are not saying anything about how the y's are distributed other than their mean and their variance. Now, if we define the sum here, this Sn sequence in the previous way, then here's what happens. We say that, or we can show that the probability that the absolute value of the sum Sn over n minus mu, the probability that that is greater in absolute value than some generic epsilon approaches 0 as n approaches infinity. Think back to Calc 1. This looks like the epsilon delta definition of a limit. That's not coincidental. Now here's the stronger form of the law of large numbers. So essentially here, if we want to make a slightly stronger statement about what is happening to the sample mean, well, we can show that the probability that the limit as n approaches infinity of the sample mean being equal to mu is 1. So in other words, the sample mean converges to mu with probability 1. So not only do we have this, well, we expect that it should be about mu, but as we take larger and larger and larger and larger samples, we will converge on that population mean mu. So this tells us that if we have a lot of data, that if we have a large sample, we should be really close to that population mean mu. Now, there are a few restrictions on this result, and here's the big one. Mu must be finite, so we have to be thinking about a random variable for which the mean of the distribution exists, and that unfortunately is not always the case. But what the law of large numbers is really truly telling us is that as the sample size n increases, the sample mean y bar will approach the population mean mu. Now, this is one of those statistical concepts that gets abused out in the real world. People say, well, according to the law of large numbers, x is guaranteed to happen. Well, yes, if your x that's guaranteed to happen is the sample mean approaching the population mean. So this is a very particular result. Now, before we end this video, I want to define a new type of distribution, one that we've actually already worked with fairly extensively, called the sampling distribution. So a sampling distribution is just the distribution of a sample statistic, and we've worked with quite a few so far in this class. The sample mean is a sample statistic, and we know how to figure out how that is distributed. The sample proportion is really just a retelling of the sample mean, so we can find its distribution as well. In the previous video, we found how to find the distribution of the sample minimum and the sample maximum. Those are both in and of itself sample statistics as well. It turns out that when the number of observations n in our sample is sufficiently large, we get a pretty nice result, and that result is called the Central Limit Theorem, which we will talk about in the next video. I'll see you then.